So here we go. Now the enlightening physics discussion that we've just ended has unfortunately not been recorded, but we're ready to begin the condensed matter seminar. So it is my pleasure to introduce one of Brown's own, at least formerly so. So Angus McMullen, our speaker, originally grew up in New York, but then came to Brown early to do his undergraduate. So he got his undergraduate concentrating in physics, graduating in 2008. He couldn't get enough of it, so he stayed on and did his PhD at Brown, working together with Jay Tang and with me. He received his PhD in 2015 and then moved back to New York to work in the physics department and specifically the Center for Soft Matter Research there, together with Jasna Bruich and David Pine. His PhD at Brown was in nanopores and viruses. After arriving in New York, there's been a recent surge in interest in viruses, it turns out. Not because of Angus, probably, but he has since moved on and started work on different soft matter systems, and he'll tell us about that work here today. So welcome, Angus.
All right, thank you very much. Let me turn my slides on. I gotta say, it is shocking to be in a talk that starts on time. There's something about NYU that, you know, we usually don't start things until about 15 minutes past. So yeah, I'm Angus. Some people may remember me from my time when I was there. If you remember me from any of my undergraduate or graduate classes, I apologize. Right now I'm at the CSMR, and I work on self-assembly. Okay, so what is self-assembly? Self-assembly is a process where a bunch of building blocks put themselves together. So imagine if your Billy IKEA bookcase put itself together. This is the world that I dream of. Specifically, I work with DNA-driven self-assembly. So the DNA acts as both a blueprint and a glue, but for us to make anything interesting, we need to also control the valence of our materials. So we need to be able to control how many things a building block can bind to, right? So if we just have unlimited isotropic binding, we may as well be stacking cannonballs instead of building shelves. So before we begin, let's begin with just a very brief refresher on DNA. I know all you know this, but in case a couple of you have forgotten, this is important. So there are 4 bases in DNA. There's 2 hybridization pairs. And if you have a certain sequence of bases, there's a complementary sequence that will bind to it with a very predictable energy that's based on the length of the sequence and also on the ordering of the bases. And this is very well understood. And these days we can buy, just order online, arbitrarily designed strands, often functionalized with all manners of different dyes and chemistries, and we can use them to attach the DNA to all sorts of different things. So amazing materials have already been self-assembled, DNA labeled nanoparticles and micron-sized colloids. The clathrate crystal on the left side of the screen has 103 particles in the crystal's unit cell, which is unbelievable. And then on the right, you have something, it's colloidal diamond. Now, this is pretty exciting for us in this department, because this was done by Dave. This was done by Dave Pine, and it was published a couple weeks ago. And colloidal diamond is predicted to have a photonic band gap. So it's almost the holy grail of colloidal self-assembly. So Dave is extremely pumped. Now, in both of these materials, valence is controlled through sophisticated manipulation of particle shape and how the DNA is attached. And for now, materials are mostly limited to periodic or repeating structures. Okay, so I am a bit of an oddball in the colloidal self-assembly field because I work with emulsion droplets instead of solid particles or nanoparticles. So I have emulsion droplets coated with DNA. Specifically, my DNA has a hydrophobic anchor, which sticks it to the droplets, and also a peg and a dye so I can see it. And then a double-stranded DNA spacer and a sticky end that allows it to attach to stuff. But what's really important is that the DNA is completely free to diffuse laterally on the droplet surface. It can go inside the droplet or off the droplet, but it's otherwise unconstrained. And the droplet can also deform. It's sticky, sort of squishy. It is sticky, but it's also squishy. Okay, so there are disadvantages to using droplets. They can coalesce if you aren't careful, and getting the DNA stably grafted to them is challenging. But there are also lots of advantages. For instance, you can use well-developed technique of total strand displacement to actually control the order in which the droplets can assemble. And another advantage of DNA-labeled emulsion droplets is that, strangely, they exhibit valence control without engineered patches. So by adjusting the DNA on their surface, you can get droplets that form only 1, 2, or 3 bonds. So we have isotropic particles that form a limited number of fluid bonds. So on the left, far left, you see a schematic of valence 1, 2, and 3. And then in the middle, that is a bright field plus fluorescence image of valence 1, 2, and 3. And you can see, so it's a mixture of red and gray particles. The red binds to gray. Red doesn't bind to red, and gray doesn't bind to gray. And you can see it's an extremely high area fraction. So if it had the ability to pick up another particle, it would. And on the far right, this is a fluorescence image where you're only looking at the DNA on the particles. So you can see that for the red particles, the DNA gets scooped up into these adhesion patches. So how on earth does valence control work in a system like this? Now, look, clearly it must have something to do with the fact that the DNA is scooped up to these patches. But in the rest of the talk, I'll let you know how it works, and I'll also show you what you can do with it. Okay, so it turns out that in theory, it is possible to have valence without patches. A paper from Don Frankel's group pointed out that you can get valence without engineered patches if you combine mobile linkers with a non-specific repulsion between particles. If you do that, then you get a limited number of bonds. Now, obviously, we have mobile linkers. A non-specific repulsion is not necessarily something we have, but this all works because you care about the energetic minimum of the cluster of all the particles, not necessarily the energetic minimum of the individual bonds. So you can get a thermodynamic control of valence just with these minimal ingredients. Now, the methods that they suggested for getting a non-specific repulsion are unfortunately completely infeasible experimentally. And as far as we know, we don't have the sort of non-specific repulsion that they're talking about. Like, there's no charge repulsion here. We're working with salt, so the DNA will work. So, you know, we're in a pre-screened system. All right, so let's take a closer look at what's going on with our droplets. So we're going to be looking at the adhesion of the droplets to a glass surface also coated with DNA that can diffuse. And this allows us to get a really good look at the adhesion patches, which you can see fluorescence images of in the top left-hand corner. Now you can see already that there are these beautiful rings. And we can also measure the area of these patches and their brightness. And from that, we can make a parametric plot of patch area as a function of the number of DNA that we estimate to be inside the patch, which is this plot here. Now, the different color points represent different preps of particles that have different amounts of DNA on them. So dark blue has the least amount of DNA on them, and magenta has the most amount of DNA on them. And immediately we see something strange. So if the DNA were to simply recruit into a patch until it was close packed, we would expect the patch density to saturate, while the patch area would continue to grow, because it grows until it reaches a maximum density in density, until it reaches maximum density, and then it'll grow its area because it's at a maximum density. But that's the opposite of what we see. So we can see from the schematic what's actually going on. We get some physical intuition. My droplets aren't deforming. So me mentioning that they're squishy is true, but it's sort of a red herring. And my DNA, because it's double-stranded, is essentially a bunch of rods. And they organize themselves as best they can, forming a ring. So to get some analytical results, instead of just physical intuition, my collaborator, Sasha Hickelfeld at the University of Illinois, built a free energy model. So it's composed of the binding energy for the DNA, the configurational entropy, the molecular spring energy, and the DNA-DNA interaction energy. So this free energy model is a patch-centric model. It's really only looking at the patch. The binding energy turns out to not matter that much. It mainly governs the proportion of DNA inside the patches versus DNA outside the patches, but doesn't really change the plot that you see above. Instead, what we have is a competition between molecular spring energy, which wants to keep the patch small, and DNA-DNA interaction energy. It's just an Onsager interaction, which wants to spread the patch out. And that results in this black curve here, which fits data very well, and amazingly has no fitting parameters. That's just a prediction. Okay, so this is a schematic of a sphere resting on a surface. So we have the radius of the particle, R naught, the length of the DNA, L, and the radius of the circle that would make, the sagitta, is RP. And we can vary different parameters and see what we get. So if we change the radius of the particle, R naught, if we increase it, then we get the same shape distribution, we get the same plateau, but the height of the plateau just increases as we increase the particle radius. And if we increase the DNA length, same general thing. Increasing the DNA length, we just get the same sort of shape and increase the height of the plateau as we increase the length of the DNA. Now, if we do a little bit of geometry and recognize that R naught is much, much bigger than L, we can actually just plot all of this data onto a single curve. So if we estimate the plateau and plot it as a function of the DNA length times the droplet radius, everything collapses onto a single line, which is, so everything's just geometry in terms of this plateau area. The only point that falls outside that line is that red point there, which is the longest DNA length we have. And that's actually expected because at 130 nanometers, we're getting above the persistence length of double-stranded DNA. Persistence length of double-stranded DNA is 50 nanometers. So it's no longer actually a stiff rod there. And our full analytical model, the red line, still nails it bang on. So we understand what's going on pretty well, I think. Now we can also look at the patch profiles, the concentration profiles of patches. So this is an image of a adhesion patch from kind of the onset of growth, the lowest size and density that we see. And the black lines are randomly selected experimental profiles, and the red line is the theory, again with no fitting parameters. And then if we look at near the plateau, we see rings. Okay, so again, this is about the competition between the molecular spring energy, which is dominating when you're small, and the DNA-DNA interaction energy, which dominates when you get bigger. And we can do even something much cooler. We can put two different DNAs of two different lengths on the same particle. And when we do that, and we look at the adhesion patch, we see concentric rings. So the DNA is that's green is the shorter one, and it goes on the inside. And then the DNA that's the longer one is the red one, it goes on the outside. Okay? Right, so now that we understand adhesion to a surface, we can look at adhesion between droplets. So here are 5 images, valence 1, 2, 3, 4, and 5. You know, we can see the adhesion patch. We can get a rough idea of how big it is, how bright it is, and also how bright the perimeter of the droplet is. So how much DNA is recruited versus how much DNA is not recruited. And we can do this on a per droplet basis. Now, I can do the same sort of plot as before. I can plot the patch area as a function of the estimated amount of DNA inside the patch. I get the exact same thing, even though this is now droplet-droplet instead of droplet-surface. It's a little, the scaling is just a little different, right? Everything should be the same. It should just be off by a factor of 2, because surface, and then imagine a droplet here. And again, we get very good agreement between experiment and theory with no fitting parameters. And if we look at the ratio of DNA inside the patches to DNA outside the patches, which is a rough proxy for the effective binding energy of our system, it seems that the binding energy of DNA in our system is low enough where our patch is likely thermally equilibrated. Okay, so now we can look at the actual measured valence as a function of the estimated DNA per droplet. So the red outline markers are equivalent to the different DNA preps. So the red outlined dark blue one is the same as the dark blue points I showed before. And the red outlined magenta one is the same as the one I showed before. So it's the different ends of how much DNA I'm putting on the droplets. And you go from valence 0 almost all the way up to valence 5. So it's a little bit disjointed. We have worse control over valence the lower in valence you go. But if you look on a per droplet basis, so instead of plotting the average valence, we look at all the particles that have valence 2, and we say roughly how much DNA is on them. That's the blue points. So the blue points are the valence plotted as a function of the average DNA per droplet. And that you get a really nice linear trend in the very beginning, which tails off as you get to higher valences. Now, I should probably tell you, for those of you who are following along, this is 2D. This is a 2D assembly, and I do this for pure convenience because it makes the data analysis infinitely easier. The downside of that is that we don't have great confidence in valence once you get above 3, because then you start getting geometrically frustrated. You know, in fact, you should be able to pack in 6, and I never saw, I saw valence 6s like 4 times. It's unlikely. Okay. Now, what I can do is we can plot the average DNA per patch. So not just per droplet, but per patch. And that's this plot right here. It's the blue. And we have a theoretical expression for the free energy of the patch. And we can ask, what is the free energy of a multiple patch system? And it turns out that you have an energetic minimum. So there's a thermodynamically defined valence where a given number of DNA is preferred to be distributed among a set number of patches. So the patches grow until you reach a critical density, and then they'll want to seed other patches. And the predicted DNAs per patch for valence 1, 2, and 3 are those black squares. And again, this is plotted with no fitting parameters. So we're a little bit outside the error bars, but considering the number of assumptions that I had to make to put this in the same units, I think that this agreement is absolutely spectacular. And now I can go even further. If you're completely unconvinced, I can go even further. Now, let's say I take a valence 3 particles. That's this blue particle here. Now, it's going to stay in the center of the screen because I'm tracking it through the whole movie. And it can bind to any of these red particles that's Now what I'm going to do is I'm going to heat the system up, I'm going to melt those bonds, and I'm going to cool it back down, and let's see what reforms. So let's start the movie. These things start diffusing around. The number in the top right is the temperature. It's 27 degrees, 28 degrees. So now we're going to ramp it up. We melt them. They completely reshuffle. And then it reforms 3 bonds. And I can do this quantitatively. I can take a whole field of view, and I can look at the valence before melting and the valence after melting, Zi and Cj. And if I subtract them, I get a histogram with a massive peak at 0. So our valence seems to be, which is absolutely crazy, maybe thermodynamically controlled, and it is certainly reversible. Okay, so what can we do with this? Well, we have droplets that can make a limited number of flexible bonds. Let's make polymers. Let's make a bunch of particles that have valence 2. And that's what we did. So this is a flexible droplet polymer that is 20 monomers long. And again, it's rough. This one's quasi 2D, not 2D. And it's browny and it's moving around. It's relaxing. It's having a good time. Okay, so we can show that the bonds are freely jointed by taking a bunch of trimers and just tracking them over time and looking at the angles that bond forms. Now, if the bonds are freely jointed, the histogram of explored angles should be flat, which it is. There are values which are not allowed, but that's just because of excluded volume. And as any good physicist will do, even though some people confuse me for a chemist or a chemical engineer these days, the first thing that we're going to look at is the polymer structure. So we're going to look at the scaling of the end-to-end distance with the number of bonds. Now, in 2 dimensions, the Flory exponent should be 3/4. And B should be the Kuhn length, which should be a monomer size. And that's pretty much exactly what we get. We get n to the 0.72. Again, this is only the n equals 20, but still pretty spectacular. And we can also look at the polymer dynamics. So we can track the self-diffusion of polymers as a function of length over time. And what we would expect is an exponent of 3/4 for polymers with hydrodynamic correlations. If they didn't have hydrodynamic correlations, it should be 1.
Is this done near a surface that might lead to hydrodynamic?
So that's a very, very good question. And the answer is yes. And so, yeah, naively, I would expect a scaling exponent of 1. And why there's a deviation is more than likely, we're not going far enough out in n. And you can even see, you know, that the error, you know, the self-diffusion is a harder measurement than the end-to-end distance, mainly because you need to watch it for much longer than its relaxation time to really get a sense of what the diffusion is. So that could be a complicating factor. We've started field assembling these. So now, you know, self-assembly is a little slow, and so it's a little dirtier. So you end up with like max 20, and we've been field assembling them, and you can get like hundreds of monomers long. And so I should be able to tell you what the actual scaling is because I literally have the data. I just have not bothered to look at it. But yes, it's right next to a glass surface. So you are right. Okay, so now what do we do with these polymers? Like we have colloidal polymers. It's a fun little toy system. You know, it's cool to look at. But you know, I mean, you can do any of that with a computer. what can we do with these that we couldn't just do with a computer? Well, we can try to make complex colloidal materials through folding. Now, if you want to make a complex colloidal material, there's two different ways to do it. There's the jigsaw approach, which is the one on the left, and then there's folding approach. So the jigsaw approach is pretty straightforward. Basically, you have a big puzzle, and it's got a certain number of specific and directional interactions that encode the piece's location inside the puzzle, right? And it assembles into the material that you make. Now, the design of this is a little bit more straightforward in principle, but the number of specific and directional interactions that you need scales really unfavorably with the material size. It is also subject to pretty bad kinetic traps. The other approach is the folding approach. And this is obviously the approach that nature takes. So, you know, proteins in biology are polypeptides, linear polypeptides that fold into a functional three-dimensional shape. So in that approach, you have a flexible polymer that has a sequence of interactions. And that sequence of interactions guide its fold into the desired structure. Now, the design of this is not as straightforward. And, but in principle, you could design this to avoid kinetic traps. And that's actually what they think happens in nature. Okay, so we have all of the requisite ingredients to start doing this. We have a flexible polymer. We have programmable secondary interactions, which I'll talk to you about in a second. And we need the polymer to be Brownian, which it is. It diffuses around. The only other thing that we need is a sequence, and that's a little bit more challenging. Right now, what we can do mainly is homopolymer, which is one sequence on the chain. That's the all blue one on the left, collapsing into clusters. Or we can do an alternating sequence. So you can put any arbitrary, you can have an arbitrary interaction matrix, but only with an alternating sequence. Okay, so secondary interactions, how does it work? Well, we put together the backbone, you know, the polymer of our chain with one kind of DNA. And that DNA has a melting temperature about 65 degrees. So as long as we throw in other DNA strands that we can design so they don't interact and don't interact with the backbone, as long as their melting temperature is below the melting temperature of the chain, we can do whatever we want, right? So here we have a little Pentrimmer, and it's got a secondary interaction, just DNA, another kind of DNA. And what it does is it clusters them together. I go up above the melting temperature, it unfolds into a linear chain, and then I can ramp the temperature back down, and it refolds into a new shape, a new cluster, okay? This is totally reversible. You can just flip the switch over and over again and do whatever you want. All right, so let's look at the simplest possible thing that we can fold and see if we can learn something interesting. So the simplest possible thing is a trimer, but there's nothing you can learn from a trimer. So the next simplest thing is a Tetramers, so 4 particle long polymer. And we're gonna do this in 2 dimensions. So the gravitational height is such that the particles are pressed up against the glass. And I do this to make the data analysis easier. It does not have to be this way. It just makes my life easier. And the interaction matrix of this polymer is homopolymer. So red likes red and orange equally, and orange likes red and orange equally. And so as I go up and down above melting temperature, this polymer folds and unfolds. And if we do this for a whole lot of different tetramers, we can overlay their folding behavior onto a single plot, which is this plot on the bottom. So this is just a single state parameter. It's the end-to-end distance in monomers. And the gray trajectories are the end-to-end distance of a whole bunch of different polymers, and they're just the ones that are not finished folding yet, whereas the red points are from polymers finished folding. So it explores all manner of different configurations, but then finally collapses into two different distinct folding configurations. Okay, so let's change the sequence slightly. And we have the same thing. So we have Tetramers. But this time, red likes red more than it likes blue. And blue likes blue more than it likes red. And the blue-blue interaction is stronger than the red-red. So blue-blue turns on before red-red turns on. And I can do the same thing. I can flip the temperature up and down and see what happens. But now, because of these very simple design rules that I put in place, we only get one final configuration. So if we look at them side by side, on the left, with just a simple homopolymer, we get two configurations. And on the right, we get a single configuration. So we can control the folding pathway, even with the very simplest of sequences. So this means that, in principle, we can have more complicated colloidal clusters that we can fold, say, into chiral structures that can do all sorts of amazing things just by carefully controlling the simple design rules and the temperature protocol that we employ. All right, so that was, I went through that a little fast. It's hard on Zoom because there's no audience, and I don't get visual cues. But the plus side of that is that now you guys get more time for the rest of your day. So thank you very much. And I'd like to thank everybody in the Bruchik Lab, the Pine Lab, the Center for Soft Matter, and all of my various collaborators. Thank you.
Okay, thank you, Angus. All right, so this does leave plenty of time for questions, which is good. So let me open the floor for questions. And because screen sharing is currently happening, I can only see a small subset of people. So don't hesitate.
Would you like me to stop screen sharing?
Yeah.
Maybe, yeah, let's try that for now. That way we'll see the gallery. Right. I think I see everybody who's on. Yes, Richard.
Yeah, hi. So I was thinking about the analogies between the folding principles for your artificial colloidal particles and for actual proteins. In the protein example, there's a sort of simpler idea than you're using. Instead of having multiple interactions to guide everything, connecting with everything, mainly there's on and off. And so that you have polar groups tend to associate with polar groups and non-polar groups don't care. And so it's because the solvent plays a role. And so in terms of thinking about making the analogy, can you play with that too? Can you actually make it so that, just have not two different kinds of interactions, one kind of interaction, but that the solvent will automatically tend to compress pieces together that don't have that interaction?
So yes, absolutely. So you're talking about like kind of the HP model, right? And yeah, that's like the simplest thing we can do. We're often accused of trying to be more complicated than nature. One example of that is that when nature makes a protein, it has a ribosome assemble the polypeptide, which turns into the protein. We're trying to make polymers that self-assemble themselves and then fold. So we're trying to be.
I don't think my question had anything to do with the ribosome. It just.
No, I know, but I understand. I'm saying that yes, in terms of testing that sort of just on-off interaction, most of our interactions are just on-off. When you're talking about colloidal DNA interactions, doing on-off is easier than doing a tuned energy, because the melting curves are very sharp.
Yeah, so the reason I was asking, I was wondering, if you think about the free energy landscapes of the two different approaches, I can't think off the top of my head how they're going to be different, but there probably will be, and there'll probably be different kinds of kinetic traps in them both, and different abilities to create different structures in both. And the comparison might be interesting.
So we are looking at that in a simple. It's not exactly the same, but because the DNA interactions are so sensitive to temperature, one of the nice things you can do is you can anneal the system, and there are differences even in a simple with one interaction. Even if every bead on the chain has the same interaction, and it's really just polymer collapse, not a hydrophobic, or hydrophilic collapse. It's just if you have, for instance, a polymer that is 12 units long. If you do a fast quench, there's a bunch of different configurations it can fold into. But if you anneal the system, there's only one. So there's definitely a dependence that we're exploring on the quench rate and the annealing and the strength of the interactions. But it's a pain.
Other questions from the audience? So regarding the temperature dependence, Angus.
Yeah.
I can imagine that you can have a whole sequence of things that you decide. I want to put these parts together first, these other ones. So you can sort of program in the little IKEA person with the question mark and the handy tool in those orders ordered by temperature. So the first thing that we would want to form is obviously the backbone, and then the second thing would be a next order structure. How far along have you proven out that concept? Like, how many different temperatures have you seen at work in a system? And then what's the most sort of advanced thing you would imagine putting together? Or what principle of design would you apply? Do close things have to come together first? So you're making modules, and then these are getting bigger and bigger, or is there some other design?
No, that's a good question. Okay, so first I would say that the most complicated. So it depends on on what your sequence is and how many different flavors you have, right? So right now with the building blocks that we're working with, there's only two. There's red and blue. And so you have, you can really only have three different interactions that aren't the backbone, right? You can have red, blue, or blue, blue. And we have managed to do that. It's actually what I just showed with Tetramers. Now, in terms of added complexity, so you can start to add more identities in that chain, right? So instead of AB, you can do ABC, ABCD, ABCD, that kind of stuff. As long as it's repeating with this method of assembly. And you could get arbitrarily complex things, but you're never going to get something really complex when you do it that way. But there are people who are interested in doing that. For instance, collagen has, there's some, Michael Brenner at Harvard is really interested in these sort of repeating polymer sequences and how they would braid themselves together. So there are things you could do like that. Now, in terms of fancy things that you would want to make, the first thing that you would try to do is to make something that was chiral, and you would have to have something that would break the symmetry. So you would either have to have domains or patches that you would engineer on the droplet, which we've done. Or you can do more subtle, elegant things like using external fields, just like gravity, to break the symmetry. You know, so you can assemble something in 2 dimensions, then flip it upside down and let it explore the 3rd dimension and see what it turns into, that kind of stuff. Now, if you can make something that's chiral, you can make something that is optically active with polarized light. You could make something that swims with polarized light. You know, you could imagine a material that could fold and unfold into the 2 different polarities, and so it would swim one way and then another, depending on the external stimuli that it was given. You know, but in terms of, you know, killer applications, you know, things that you would, you know, like bookcases, you know, we're not really there. You know, everybody in the field, people were really excited like 5 years ago to make sodium chloride crystals.
You mean with 2 different types of particles to be able to make that kind of
getting the interactions to cleanly work, like to not have sticking, to not have you know, really bad kinetic traps is actually pretty challenging. And you know, and I mean, really, when I showed up here in this department, and I would say that people in this department are it's not an exaggeration to say that this is the best department in the world for colloidal self-assembly, between Dave and Paul. You know, between those 2 people, it's pretty much bar none. When I first showed up, when I had my job interview with Dave, he was showing me, really excited, just super excited. He was showing me movies of just crystals forming out of simple isotropic interactions. So in the time I've been here, he went from being extremely pumped about getting just basic salt crystals to form out of colloids to making the diamond. So you know, the field is sort of accelerating right now, and it's starting to look like technological applications might be possible. As of right now, the only ones that people have really thought about beyond just the philosophical idea of self-assembly, which is what I'm mainly interested in, mainly focus around optically active materials. So materials that have really unique properties of light, because a lot of these things are the same wavelength of light. So they can have really, really bizarre properties, you know, like negative index of refraction, things like that.
But you now have like a system. So with the emulsions,
Yeah.
you have a system where you have liquids in their own little containers that you can bring together in programmed ways. I mean, have you been thinking about things like, you know, using the power of that to do biochemistry or analytics, or I mean,
Yeah. So the paper that I mentioned very early in the talk, this idea of doing doing very simple DNA computation on droplets to guide their assembly. So what you know, Paul did, and I was a co-author on the paper, but I didn't do that much. What Paul did was, you know, he took the basics, the very, you know, floor basics of DNA computation, and overlaid them onto the self-assembly of these droplets. And that's all he did. He did it as a proof of principle, and never went any further. But there's this enormous field of DNA computation, and all these people do is do things in soups. You know, very slowly now you're starting to see people do it on DNA origami scaffolds. But the number of people who've combined this with you know, particle self-assembly is like, there's like one guy in France. And he does it in a very, very limited way. So you can make you can make oscillating chemical networks that can you know, change these particles' valence over time and space. The number of things that you can do are endless. And you know, one thing I'm really excited about trying in the future is, you know, like we know that the DNA that the DNA can communicate between droplet and droplet, and being able to send signals, DNA signals down the colloidal polymers, and possibly be able to implement decision making along that polymer, all spatially confined, not in some big soup, would be a lot of fun.
Jay, you're muted. You're still muted. Okay, let me ask you to unmute. So.
Sorry, I need to unmute myself. Yeah, so think along the line of applications, right? And
yeah.
I know you're sort of trained as a physicist, think about this bottom-up self-assembly, but for, you know, chemical engineers, right? Think about from material science point of view, right? What if you, I don't know if you can make large, you know, amount of this material. What do you think about just, you know, a soup and giant mix, right? In terms of you know, rheological behavior, or using this as a way of sort of mixing materials?
Yeah, so so we haven't really gone into the rheology of these materials too much. We can make them in bulk now, which we couldn't before. The only reason why I think we haven't looked at the rheology of them is just that I only have two hands. I think it's one of those things that is absolutely a target. You know, if I were to make them for that sort of thing, I wouldn't self-assemble them. I would field assemble them. Which we can do, yeah, we've talked to a few different collaborators about doing the rheology of dense suspensions of colloidal polymers, but
right here you have very precise control of, you know, whether or not having branches, right?
So you can definitely control that. Precise is a strong word.
Sensitively.
Yeah. So in terms of on a population level, yes, you can control the percentage of branches to a reasonable degree. You could be able to control them in a much more engineered way if you thought about it, I think. So there's definitely that, and you know, I had a thought and I just lost it. But yeah, you're absolutely right. It is something that, you know, people have expressed interest in. It's just not something I've had the time for, unfortunately.
Yeah, I mean, a lot of things you can do with it, right? I mean, extraction is another possibility, right? Because you have the DNA and, you know, this oily droplet stuff, right?
So you can make them without. So if you field assemble them, you can make them without DNA, and then you can make them with covalent bonds, and you know, then you just wash them. Then they're stable. You know, one fun thing that happens when you can do that is we have some preliminary data that shows that actually the fluidity of the bond is is actually contingent on the particle not deforming. So if you lower the surface tension quite a bit, which you can just do by dumping in surfactant, you can make them squishier. And then this happens particularly if you're not using DNA. When they bind and when they assemble, you can change how stiff the polymer is just by changing the amount of surfactant, which should definitely change any sort of mechanical properties that a dense suspension would have.
Sure.
Yeah, so there's a lot of cool stuff that we could do, but I mean, we're not getting any grad students anytime soon in this department. So it's just me.
All right. If there are no more questions, all right. So I will ask the.
Can I actually ask something quickly?
Oh yeah, sure. Go ahead.
So I was also thinking about the analogy to proteins, and so you mentioned how, and you showed with videos of just 3 of the connected droplets that they really are freely jointed, right? But proteins are not really freely jointed, right? I think between each amino acid, there will be just a few fixed angles it could take. So is there a way without sort of complicated secondary interactions that you can fix the available angles?
Okay, so first of all, very good point. People have actually done simulations on this. And, you know, there's some Italian guy who's done a whole suite of simulations where he's tested out exactly what the bare minimal ingredients are for some beats on a string models. And you do need some sort of bond angle on your secondary interactions to make any sort of arbitrary structure. So you can make some structures without a bond angle, but to make any structure, you need some bond angle on your secondary interactions. Now, there are, in terms of simple ways to do this, no. Complicated ways to do this, absolutely.
Yeah.
There are, people have used, a friend of mine used DNA origami to make a defined angle. So he wrapped DNA origami around a colloid, and then, it's this big, huge structure, and you can, since it has defined binding points, you can actually define exactly where, all 4 particles in a tetramer would go.
Right.
You could do other things like domains or rafts, which we've done. So there are things you can do to push that, and it's absolutely something that we're going to work on, and that we are working on. But there's no easy way.
Yeah.
Nothing is easy.
Right.
But it's a very good
Thanks.
question. It's a very good question.
Thanks.
I have maturity. Nothing is easy.
All right. Are there any other questions? Last lingering ones? Going once? Going twice? So since there are no other questions, I want to send you my Zoom applause. I invite the remaining few to do the same. So thank you, Angus, for an interesting and stimulating talk. And thanks, everybody, for showing up.
Thank you.